Today's stream is going to be about dynamic allocation in Rust, and this is going to be a pretty quick one because there's not much to cover. It's just something that I wanted to put together in a video and have it somewhere on the internet. So dynamic allocation in Rust, when we talk about dynamic allocation, obviously we're referring to allocations on the heap, which means allocations that happen at runtime. And we're not referring to stack-based allocations or static memory, etc. So at runtime, for runtime allocations, what you need to do today, what happens is, if you were to sort of use the standard library in Rust, you pretty much get this allocation stuff, as part of the standard library. Obviously, you're not going to write your own dynamic memory allocator when it's already something that the language provides, or rather the standard library for the language provides. But if you want to go ahead and implement this, like you wanted a custom memory allocator, and when I'm going to use the word memory allocator, when I say that, it basically refers to the heap. The way you do that, so think of a scenario where you're working in a no standard environment. There's no operating system, so there's no operating system provided malloc or other kinds of memory allocators that the kernel offers, because there's no kernel, first off. So in that case, how do you actually build your own memory allocator? Well, here's what you do. In Rust, this is sort of pretty well defined, I'd say. You define a static, and that static is basically your memory allocator, provided you do two things. You decorate that with something called the GlobalAllocator proc macro, as you can see here. And then that particular static also ends up implementing something called the GlobalAlloc trait. Now, the GlobalAlloc trait is, very simply put, it defines the functions that a heap allocator must provide. What does a heap allocator generally do? It basically allocates and then it deallocates. That's like the two primary things that you want it to do. But here's the thing: once you do both of them, you don't have to actually say allocate or deallocate. You don't have to explicitly call allocate or deallocate the methods in the GlobalAlloc trait. The compiler automatically inserts that in there for you, so that's cool. Now, the other thing that we should also keep in mind is that the GlobalAlloc trait, the alloc and the dealloc methods that are part of the GlobalAlloc trait, they are pretty much unsafe. Obviously, because if you, in the case of the standard library provides the implementation for the alloc and the dealloc. In your case, if you're building a custom allocator, you have to provide that. So obviously it's going to be unsafe. But beyond that, there's also another important reason for why that is. I think I'll come to that in a minute. So both alloc and dealloc take, let's actually look at the trait itself and see what is included in the trait. I think I have it here. Yeah. So yeah. So GlobalAlloc, this is what it looks like. It's got the alloc method. It's got the dealloc method. It takes a type called layout, and both of them take the type layout. So basically, layout talks about the layout of the allocation or deallocation that you want to perform. Allocation, the alloc method ultimately returns what's a raw pointer, a mutable pointer to the allocated memory. Dealloc pretty much takes that raw pointer and takes the layout as well and does the deallocation. Now, the implementation of that is something that you have to deal with. But if you remember, I mentioned that you have something, I think, yeah, it's right here. So you end up, this is basically your allocator, aptly named allocator. So this is a simple allocator that's been defined. So the idea is that you basically say that you decorate that with this particular proc macro, and then you have to implement the GlobalAlloc trait for it. That's about it. And then you now have a custom allocator for yourself. Of course, it's, obviously not that simple, because when you actually talk about allocations and deallocations, you also have to take into consideration the fact that, are you operating in a multi-threaded environment or in a concurrent setting? If you are, then you need to take care of, who has, because there's only one allocator that's doing the allocation, obviously, that needs to keep a track of how much memory has been allocated and where is that memory, all of that stuff. You could have multiple threads requesting for allocations. So you need to figure out, how you deal with that. And the way you do that is you pretty much use some sort of synchronization primitive. But remember, I mentioned that, both these methods are actually unsafe. The reason for that is because we are actually declaring that this allocator is a global static. And in Rust, technically, if you want that to be a global static, you can only have immutable references to it. But, in our case, we'll end up needing a mutable reference to the allocator if you want to pretty much, actually do any allocation or deallocation. Keep that state, that is. So what do we end up doing? We'll end up using some sort of interior mutability. Specifically, we'll end up using some sort of synchronized interior mutability. In other words, we will simply put that allocator in a lock. And, that way we can go ahead and, have mutual exclusion access. That means one thread has the lock, it has access to the allocator, and the other one will have to wait for the lock, etc. Basically, that's about what we'd want to do. I'm not getting into all of this implementation. You could probably read your own, all of that stuff. So there's different kinds of implementation that you can do. But let's actually take a look at what that means. So the design goals of any allocator is you return, basically, when you do an alloc, you're actually returning unused memory. And when you do a dealloc, you keep a track of the memory that's been freed. Okay, so those are the primary basic things that you need. And the most important thing is you never hand out memory that's already in use. That's these are the basics. You have these three, then you've got a working allocator. Then on top of that, you have a lot of secondary goals, like you want to efficiently use memory, which means fragmentation needs to be low. You don't want blocks of your heap being allocated and deallocated in such a way that you can't end up, doing new allocations, because the heap is very fragmented. Obviously, it has to work well in concurrent settings. And then you also want it to be more performant as possible. You want to hit the targets like cache-locality and avoid false sharing and all that, but those are all secondary goals. And just to sort of talk about some implementations, some ways of implementing a memory allocator, there's many variants. The Linux kernel has things like the slab allocator, and the buddy allocator, the VM allocator. It's got a bunch of different things for different purposes. So case in point, there is no perfect allocator. Every allocator is tuned for the workload that you are targeting, right? And the other point is, whenever we talk about bare metal systems, the reason I'm talking about this is because I'm looking at implementing my own custom allocator for a particular project in a no standard environment where there's no operating system, obviously. So you technically, in regular systems, you'll have an MMU, which is a memory management unit, which means you map virtual memory addresses to physical memory addresses. So you need to do that before you actually do your allocation and deallocation, obviously. You actually take a virtual range of memory and then you map it to physical memory. Only after that would you, go ahead and actually do any allocation. Makes sense. Without an MMU, you don't have that mapping step. You don't need that because you're accessing physical memory directly. So there's no need for that. Let's take a look at the bump allocator. This is one of the most simplest ones. This is something that we'd end up using in what you would call arena allocators. Now, arena allocators are sort of a simplification of a general global allocator. We'll talk about that. But in a bump allocator, it's very simple, as the diagram shows over here. You have a heap start and you have a heap end. So the next pointer, the one that you see here, this is the next pointer. It always points to the next byte of unused, basically the next byte of the unused heap. That's it. And the pointer only moves in one direction. All right. And then you keep a track of memory. You also have the allocator also, keeps a counter as its state, so that every time you do an allocation, you say that, okay, these many allocations were performed. And then every time you do a deallocation, you also decrement that, saying these many deallocations were performed. Right. So that's pretty straightforward. It's, as you can see, it's going to be pretty fast. There's not a lot of state. There's not a lot of stuff that you need to keep a track of. You just keep a track of, the thing that's pointing to the unused byte first. So obviously it's not very flexible. In this case, the biggest disadvantage is that although it's very fast, it can only reuse memory after all allocations have been freed. So you pretty much, once this is allocated and stuff, you can't simply say, okay, my next pointer is going to move back and then I'm going to start allocating stuff. That's not, how the bump pointer would. That's why it's called the bump pointer. You just keep bumping the pointer to the end of the, the allocated stuff. And this also makes it very, very useful in scenarios like arena allocation, which, let's see if we can get into it, because I just want to keep this short. And yeah, this is not used as a global allocator. What you end up using as a global allocator is this thing called the linked list, and this is again a good diagram over here. The linked list is nothing but you end up putting a linked list in all the freed up regions of your, heap. So all the colored ones over here, whatever color that is basically used or allocated space, and anything that is not allocated actually has a linked list node in there. So this is one, this is one, this is one. So what happens is whenever you free something, you put another node in there. Whenever you want to add or you want to allocate some space, you remove a node from there, right? So that way you can end up doing things like directly reusing freed memory. And it uses the freed memory blocks to create what is called, basically it's a linked list, but it's also called a free list because all the free regions are being tracked with that list. The list makes it possible to store an arbitrary number of freed blocks of different sizes. You don't have to worry about that. Obviously, there's a problem with this. Again, the disadvantages are you obviously suffer from poor performance because every allocation requires that you completely traverse the entire free list, right? And then it could also lead to fragmentation issues, which I don't think I have a diagram for, but anyway, you would end up in a scenario where okay, let's not get into that. As I've said over here, let's say you have two adjacent, you can say, blocks of memory that you've freed up. Technically, unless you do something called merging, you can't think of them as one block, although they're adjacent. So what you do end up happening is you end up running out of memory space when you build your allocator using this design approach. All right. And then the last one is pretty much the one, or variations of this is what you end up using in production, or actually in production. In the Linux kernel, there's a lot of stuff. There's like the slab allocator and the buddy allocator. There are variations of this. The underlying theme is basically this, as I understand it. And this itself, the fixed size block allocator, is basically a variation of the linked list one. It still has you still put your nodes in the free parts, but what you do is you don't have one list, you have multiple lists. because you break up your heap into different block lengths. So you have like this particular block is all broken up into even pieces of 16 bytes each. And then the next one is all 64 bytes till here. And then the next one is all 512 bytes. So you keep doing that, and then you basically end up tracking each one of those lists and saying, okay, let's for each block a separate free list exists, so that all the allocations and deallocations only need to insert in that particular front of the list. And that technically actually makes it faster. But yes, what's the downside? The downside is that you do sometimes end up, if let's say you had like a 64 is the second one, you have 16, 64 and 512. If you had something like a 128 byte allocation that comes up, you would end up using a 512 byte, the 512 byte list. And that means you'd end up pretty much fragmenting your heap by half of it. So yeah, that's also the case here. So pretty much you can have these design approaches. You can have all these design possibilities that you can do. So in my case, what I was actually thinking about was I was trying to look for, what does the standard libraries vec type, which is what we call, sorry, let me just go back. It's a standard vector. So basically it's one of the collection types in the standard library. As you can see, it actually, in its type signature, you have, what kind of allocator is actually doing the allocation. So the allocator has to implement the allocator interface. So if you remember, I mentioned that there's something called the GlobalAlloc trait and that decorator. This allocator is another trait that actually wires this type up to the GlobalAllocator trait methods that you implement. So if you just follow the type over here, you see that it has the allocate methods and the deallocate methods, but the instance of the thing that implements the allocated trait that's actually doing the allocation over here is global. So if you go to the global definition, you will see that it actually implements, where is that? Yeah, it implements the allocated trait, which is global implements the allocated trait. And if you call the allocate method on that, in other words, it calls alloc_impl, and alloc_impl in turn calls what is called the actual alloc method. The alloc method over here is like a standalone function. If you just read the documentation for it, it says it allocates memory with the global allocator. So in other words, the allocator API is sort of like a nice little abstraction that helps you call into the global allocator that you want. In other words, you can switch out your allocator very easily. And that's why we have this allocator API in between. Right? So that's in a nutshell what I wanted to cover. But also, there's something that caught my eye, which was interesting. There is a project called Talc, which is, I was wondering if I have to write this all by myself. It's going to take a little, I really have to think about a couple of things, because allocations and deallocations that you see in the different designs, they are not very simple. You could have a bunch of different things. You could actually go ahead and do things like boundary tagging and all of that stuff. And yeah, if you don't want to implement that, it's good, unless it's fun. Okay, so what happens in this is it's actually very performant according to the documentation, at least. So if you look at this crate here, so it says Talc is a performant, flexible memory allocator with first-class support for no standard. That's very important to me. And bonus, you also talk about WebAssembly, which is interesting. I'd like to look at that. So it's very simple over here. I was just trying to test this out. As you've seen before, the allocator is here. It's a global allocator, which is decorated. Obviously, it's static. And then you basically, give it some memory. This is my 10,000 bytes of memory that I want to give it. It takes that, it initializes itself, you've got it. Now you've got the allocator, all right? Of course, you can definitely go ahead and jump into every single type and see what's going on, all that stuff. So Talc is the first type. and this is your linked lists head that you saw in the previous, in the fixed size block allocator. Same thing. Yeah, it's called the linked lists head. And then you basically create one of those things, and then you call the lock method on it. When you call the lock method on it, you get what is called this Talc K. It's just a wrapper, because this allows for that, you know, mutex wrap thing. So you're basically taking your allocator, wrapping it in a mutex, and then you're beginning to use it so that you get this thing called synchronized integer mutability. All right. So I think we just discussed that. But once that's done, once you've allocated it, it's as simple as, you know, then you can pull in any type from the standard library or from the core library, whatever that is, and then just get to it. So if I was to run this, just doing some testing over here, not much, everything's already written, so I don't have to do much. So interesting thing, box new, I'm just trying to print the actual address of where this box is allocated. You can see obviously it's, you know, this is the heap value. And then we're also printing some other pieces over here to do with an iterator, etc. And then also check the reference counter. All of these types are they are from the, you know, from the allocations module in the standard library. Not in the standard library, but from the allocations module, which is one of the modules that is also included in the standard library. So you've got the core, which doesn't have this alloc. Then you've got the alloc, which contains the collections and the collection types. And then you combine both of them, you have both of them in the standard library. So you just implement with Rust, you just implement your custom memory allocators in this fashion. And you can do it for systems that do not have an operating system, or, you know, obviously if you want to do this stuff is actually running in a scenario where we are using the standard library. So we're sort of bypassing the standard global allocator that is part of the standard library. So both cases, we can actually do that here. Okay, there's stuff, I think we talked about arena allocation, etc. I think that's not important right now, but yeah, it's there. And we also talked a little bit about the synchronized integer mutability. Obviously, everything's wrapped in a mutex, so mutexes are built on atomics, and that's why you get that, you know, atomic access, or rather, you get that lock-based access to, if you want to run this in a concurrent setting. So you can do all of those things. Okay, so that's kind of what I wanted to cover. And yeah, there's a lot of stuff over here that the person's put up. He's compared it with different other allocators, like a standard linked list allocator, a global allocator, the buddy allocator, which is in the Linux kernel, and then there's some micro and there's macro benchmarks, if I saw them correctly. Yeah. So yeah, there's quite a bit of interesting stuff over here. I think, yeah, we should definitely take a look at all of this stuff. This is very interesting, so that you don't end up doing all of this. Okay. All right. That's it. And thank you.